In this class, we will discuss an analysis type of problem of beams, laterally unrestrained beams. It's a question paper problem, VTU August 2022. Check the adequacy of ISMB 450 section to carry a UDL of 24 kN per meter over a span of 6 meters. Both ends of the beam are attached to the flange of columns by double web pleat. So that means he has given the diagram like this. So it is a fixed beam, it becomes a fixed beam, at the ends it is restrained. But the compression flange of this is the ISMB section for a length of 6 meters. Total UDL can take 24 kN per meter. This compression flange of this beam, which is like this, it is not restrained. Okay, compression flange is not restrained. So therefore, finally we can take this as laterally unrestrained beam. So here you need not design. So already the beam is provided with this section for a length of 6 meters to carry this much load. We have to check whether the given section ISMB 450 is sufficient to take care of this load. So whether that strength of that beam is enough to withstand the applied load. That means what we have to do here is we have to compare the value of maximum bending moment with the design bending strength of the section. So that means MD value is design bending strength, M value is the maximum bending moment. So what we have to do, we have to calculate maximum bending moment for this beam, and also we have to calculate MD, design bending strength of the beam, using the codal provisions, and then we have to check whether MD is greater than M or at least equal to M. So if MD is greater than M, then it is safe. That means the beam is adequate. If MD is less than M, maximum bending moment, then the beam has to be replaced. So this is an analysis type of problem. Already beam is provided, we have to check its adequacy. So the procedure remains the same as that of the design procedure. So to calculate MD value, we have to use the same equations which is given in IS 800 in pages 54 to 58 or 59. Only bending value we will check. Now ISMB 450 at 72.4 kg per meter, as per the steel tables, let us write down the properties of that. So these are the properties of this ISMB 450 section. So H is the overall depth 450 mm, B of width of flange 150 mm, B is half of the width of flange, that is 75 mm, thickness of flange TF is 17.4 mm, TW thickness of web is 9.4 mm, radius and root R1 is 15 mm. Now depth of web D is given by H minus 2 into TF plus R1, which if substitute and simplify we get 385.2 mm. So these are the geometrical properties of the ISMB 450 section as per steel tables, or we can use code also. IS 800 at the end in appendix he has given the properties. Now these are the moment of inertia about the z axis, that is horizontal axis. It is 30390.8 in 10 power 4 millimeter power 4. So all the values should be in millimeters and newtons. We keep that in mind. IY, so about this beacon axis, 824 into 10 power 4 millimeter power 4. Z2Z, it is the plastic section modulus of this section, 1350.7 into 10 power 3 millimeter cube. And Z3Y about y axis, 111.2 into 10 power 3 millimeter cube. So the values are given in centimeters, centimeter cube and centimeter power 4 in the steel tables. So you have to multiply by 10 power 4 and 10 power 3 accordingly to get in millimeters. Okay. Now this is the first step. Writing down the properties is the first step. Second step, we have to check whether the section is plastic section or compact section or semi-compact section. For that, we have to use this table to page 18 of IS 800 in the table. So B by TF, two ratios we have to find out, one for the flange, one for the web. B by TF ratio, B is half of BF, that is 75, divided by TF is 17.4. This ratio comes out to be 4.31. So you can observe that this is less than 9.4 epsilon. Epsilon here is the root of 250 by Fy. We will assume this 250 for Fy. If it is not given, you can assume Fy has 250, so its value becomes 1. So therefore 4.31 is less than 9.4. Epsilon is 1 here. So then that means it is a plastic section. So you can observe from the table that if this value of B by Tf is less than 9.4 epsilon, it is a plastic section. Then D by Tw for the web. So D here is 385.2 divided by thickness of 9.4. You are going to get 40.98. Once again, the limiting value is 84 epsilon. It is definitely less than 84. So therefore, this is also plastic. So we can conclude that both flange and web, they are plastic sections, plastic sections. So therefore, the entire section is plastic section. So if it's a plastic section, this value beta B will be, we have to take it as 1. So whether it is plastic or compact, this beta B value should be equal to 1. Then next step is calculation of this MCR value, which is nothing but the elastic lateral buckling moment. So critical moment you can call. So MCR is given by this formula, which is there in page 54 of the code. This is available in page 54 of the code. This is the formula. Directly you can use that formula. Root of pi square E Iy by N square into G into It plus pi square E Iw by N square. So where N you can take this, I will take this as the N value. So that is 6 meters, that is 6000 mm. Then E value 2 into 10 power 5 for steel Newton per mm square. Even if the value is not given, better you remember the value and substitute. Sometimes you cannot give, so you have to know the values of E and G. G value is 76.923 into 10 power 3 Newton per mm square. Iy value is this value 834 into 10 power 4 for the given section. Then you have to calculate this Iw and It. So It is something but the torsional constant. Iw is called as the warping constant. So because I have told in the last class that non-circular sections, when they are subject to torsion, warping effect will be there. So this It is given by summation Vi Tiq by 3. So this you have to calculate for both flange and web. Here there are two flanges, you can see here, equal flanges because the symmetrical section. So B for the flange is this value, that is 150 into T for the flange is 17.4, that is Tf value divided by 3. So this is for one flange, into 2 we have to take for two flanges. Plus for the web portion you have to take width as this value. So that the value is this. Please note that this is the value which you have to take for calculating that B for the web, which comes out to be 450, that is the overall depth, minus Tf. So that is 17.4. That value you have to take multiplied by thickness of like this 9.4 cubed by 3. So this is there once again in page 54 of the code. If you simplify that, you are going to get this value 646572.6 millimeter power 4. The unit is millimeter power 4. So It is called as the torsion constant. Iw is the warping constant. Once again, this warping constant is given by the formula 1 minus beta f into Iy into Hy square. Here beta f will be taken as 0.5 for symmetrical section. Please note that. So into 0.5 into Iy is this value into Hy is once again this value 450 minus 17.4 whole square. If you simplify that, you get 3.9 to 10 power 11 and the unit is millimeter power 6 for warping constant. Once you get It and Iw values, substitute in this equation 1 and simplify, you will get MCR value. So MCR is pi square into E is 2 into 10 power 5 into Iy is 834 into 10 power 4 divided by L square means 6000 square, 6000 mm, 6 meters means 6000 mm. Everything should be in Newton millimeters. Then into G is 76.923 into 10 power 3 into It we got 64, 65, 72.6 plus pi square into E once again 2 into 10 power 5 into Iw 3.9 into 10 power 11 divided by 6000 square. So if you simplify this entire thing, you are going to get 180.29 into 10 power 6 Newton millimeter, which is, I can write it as 180.29 kilonewton meter. So that is the value of the elastic critical buckling moment. And now next step we have to calculate one dimensionless tenderness ratio lambda LT, which is given by square root of beta b z Fy by MCR. Once again, this is available in page 54 of the code. So if you substitute the values, beta b is 1, Zpz is this value 1350.7 power 3 into Fy is 250 Newton per mm square divided by MCR is 180.2 power 6. If you simplify that, you get 1.37. As per the code, this value, if it is greater than 0.4, so we have to consider the effect of lateral torsional buckling. So anyway, in this case it is there. So it is greater than 0.4. Otherwise, you need not take the effect. Further steps you can avoid. Phi LT is given by next formula. You have to take another parameter phi LT. 0.5 into 1 plus alpha LT into lambda LT minus 0.2 plus lambda square LT. If you substitute the values 0.5 into 1 plus alpha LT depends on the type of the section. If it is rolled section, it is 0.21. If it is welded section, it is 0.42. That is also there in that page 54. So since we are taking rolled section, so its value is 0.21. So other values, if you simplify, we get 1.5613 as the value of phi. Then next step is xi LT. So it depends on phi and lambda. Of course, if you substitute 1 divided by phi plus phi square minus lambda square to the power 0.5, corresponding values, if you simplify, you will get xi LT as 0.433. After that, you have to calculate what is called as the design bending stress. So this is the design bending stress, FBD. So this design bending stress, FBD, is given by the formula xi LT Fy by gamma mu. Once again in the same page it is there. So xi LT is 0.433 into Fy is 250 divided by 1.1. If you simplify, you get 98.4 Newton per mm square. That is the design bending stress. So from the design bending stress, we can compute the design bending strength. Design bending strength MD, beta b into FBD into Zpz. Beta b is 1, FBD is 98.4 into Zpz is 1350.7 power 3. So the value, if you simplify, you get 132.92 into 10 power 6 Newton millimeter, or it is 132.92 kilonewton meter. So this is the design bending strength. Now, after calculating the design bending strength, we have to compare that value with the maximum bending moment for the beam. So that maximum bending moment in this case, I will just write here, it is a fixed beam like this. So in the case of fixed beam, the maximum bending moment will be like this. You can observe here, subjected to UDL. So this is the beam. So if you plot the bending moment diagram for this, so subjected to UDL, so you have the BMP like this. So here you have the negative bending moment hogging, and here you will be having sagging. So you have to superimpose like this, because it is UDL, it is positive. And it is a parabola, so this is positive bending moment, this is negative bending moment. Please note that this value is W square by 12, where W is the load, W per unit length is the UDL, and L is the span. W square by 12 is the maximum hogging bending moment you are going to get, and maximum sagging bending moment will be W square by 24. So this actually we can get from the stress appliance principle. So better you remember the values. So this is the positive, this is the negative. Anyway, you have to take the maximum bending moment. In this case, maximum bending moment is W square by 12. So which is hogging in nature. Anyway, we are not worried about the nature of the moment. We are designing for the magnitude. So W square by 12. Now for this given problem, the value of W is 24 kN per meter. Anyway, I have included dead load also there. Weight of the beam also it is included, because nothing is specified mentioned in the problem about dead load. So what we will do here is this maximum bending moment I call it as M. which occurs at the supports. So M is equal to W L square by 12. W is 24. L is 6 meters by 12. So if you simplify this, you will get 72 kilonewton meter. So this is the maximum bending moment that is going to develop in the beam at the supports, of course. Now here you have to compare this M value with MD value. So MD value what we got here is 132.92 kilonewton meter. So definitely this is greater than M. So what you can say here finally, therefore the beam is safe because it is greater. So strength is greater than the maximum bending moment. Design bending strength is greater than maximum bending moment. Therefore beam is safe, or therefore we can say section, that is ISMB 450 is adequate. So this is how we have to check whether the given section for the beam is adequate or not. We have to calculate the design bending strength and compare that with the maximum bending moment. So for calculating MD value, you have to use the formula which is available in the IS 800 code in page number 54, 55, etc. etc.